Good morning, everyone. Nobody's here at this time, but I will start anyway. Today we will cover, let me see, if we look at our discussion board, today we will cover two things. We'll go over 7.3 and then Bayes' theorem. And then from there, we will go over one previous test from Spring 20 test 3. Okay. For your own study, you can see this fall 20 test 3. At that time, I give them two pieces of tests. The main one is the one in class, and then the supplements, something they need to turn in the day after. This is the solution. But for you, I will not do this. So what happened with you is the supplement part will be integrated into your in-class. Okay. Yeah, that's because in fall 20, I want them to do one new question that they never seen before. And that question tends to be kind of like big points. That's why I separate them into the supplement part. Only one question for the supplement though. Okay, but for you, no. For you, no. You will have only in-class test. The procedure for your test next week will be the same to your test 1 and your test 2. Okay, now first we will program our calculator with inverse chi-squared function. Okay, if you have not done so, please do so right now by going to this. Hold on. Oh, I'm sorry. I'm not sharing my screen correctly. I'm here. Okay, so today we will go over 7.3 and then Bayes' theorem. Okay, after that, we'll go over one test from Spring 20. Okay, and for your own study, you have fall 20 tests. At that time, I give two, the one in class and then the supplemental one. But for you, you will have only one in class, no supplement. Okay, now this is the solution for that fall 20. I happen to give the same test in the summer. Now, so for today, we'll do two sections and then one old test, okay? But for us to do this 7.3, I need you to first program your calculator with this inverse chi-square function. I need you to first program your calculator with that inverse chi-square function. Now, have you done so? I think I may ask you to do this last week. But if not, then we can do that together right now. Okay, let's do it. You click that link. Okay, I hope you're following me. Okay, if you have not programmed that, please follow. This lady make the videos in 5 minutes, and I believe she does it very, very well. You just need to follow it. But I will play the movie slower, such that basically we will do it line by line, and then I will ask if you have done that line. Okay. Now get prepared with your video, please, with your calculator, please. While we watch this, I want you to also go on. Now, you can see, you can read here, the inverse chi-square function is preloaded in TI-83 and 84 calculator. Inverse chi-square returns a critical value we use in hypothesis test and confidence interval for population variance. Now, this is the simple 3-line program that you can enter to your calculator. Okay, what do you do first? You go to program and then new and then create new. This is if you have not done it. If you have done it, if you already have the program on your calculator, you can check. Let me see. Let me show you mine, how to check if you already have that. Give me a second. Yeah. On my calculator here, you will see that I already have it. Okay. I click program and one of them is inverse chi. Okay, now, so you check first if you already have it or not. If not, then we do the program, okay? I will go back to the video. Now we will start with, you go to program, new, and then create new. Program, new, and then create new. Okay, are you done with that? Okay, if you are watching this recording, and feel free to pause the recording while you work on that. Okay, yeah, just make sure, please, you need to have this program into your calculator by next week, because you will need this in your tests. Okay, and even for the rest of this semester, you will need it. So please make sure you program this. Now on your calculator, you will see it will be with green color, and the coding, the color will be, the letters will be on the top right of, starting from math, on the top right here. That's A, and then B, and then C, and then D, E, F, G, H, and so on and so forth. Now, for you to access that, the alphabet, instead of press second, well, if you press second, you will get the top left one, right? In this case, it's the blue one. On your actual calculator, there will be the yellow. Okay, but if you want to access the green one, you will press alpha and then the corresponding letter. Okay, now if you want to keep all capital, you will do alpha lock. Look at your calculator, okay, and you will see alpha lock here, okay, which means you will get all capitals. Now, if you want to get to alpha lock, then you press second and then alpha lock, and then go ahead with the all capitals you want to type. Okay, now let me play this again. What happened? Give me a second. Okay, are you done with that? Let me play it again. So you name it with INV Chi. Actually, you can name it anything. It doesn't have to be INV Chi. You can, I actually name it IC first time I program it to my calculator. Okay, because I was so lazy. Okay, just remember which name you use. What you don't want to happen is you program it with IC, and then next week you forgot what name you give it, and then you kind of like get anxious, right? No. So let's just do it the way she does it here. Okay, so we name it. So after you get that INV-CHI, you press enter, then you get to here. Now then, we will go on with 3 lines. The first line will be this one, input, Okay, but you don't type input like word letter by letter. No, there's a function input in our calculator that we will see later on where to get. Okay, but after you press input, then you will enter this code. Okay, now let's see where to get that input. Hold on. Where do you get that input, Thomas? Let's go back again. Now, where do you get that input? You press program. You press program. So while you're here, right? You press program. Now you press program, and then after program, you go to IO. Then you go to IO, and then the first one is input. Okay, so to get that input, you go to program, IO, input. Let me play it again. Okay, let me make sure that you are done with this. Is it okay? Can I go on? Now then, the second line, we will do pretty much the same thing. You go to program, IO input, and then you alpha log that with then code DF, that stands for degree of freedom, and then colon, and then close quote, and then exit alpha mode, comma, the comma is above 7, right? And then go to alpha mode again with D. Okay, let's make sure we get it. Okay, before we go on, the colon needs to come before the closing quote. Okay, the colon needs to come before the closing quote, not after. You cannot reverse that. Now, let me make sure you are done with that. If not, then you play this video again. Actually, you can just play that video. Okay. It takes me, if I were the one explaining this, okay, trust me, I will do a lot worse job. In fact, this lady who make this video has been updating this video many times. Okay, when I saw this video like last week, just to make sure that that's the video, it turns out that the name of the author already changed, and it was done like around how many years ago? Only 2 years ago. But this original video was made like around 5 or 7 years ago. Okay, this video already long time, but then she apparently keep on updating it. Okay, to make it clearer, I believe, right? Okay, now so but she can do much better than me. Trust me. Okay, so display DISP is program IO DISP. It's in the same category with input, but it's number 4 instead of number 1 for input. Let's start again. Yeah, so the display DISP is actually number 3. Input is number 1. Let's go on. Where to find that solve? Okay, so to go to solve, let me grab my my calculator. Where to get that solve? So either you play that movie again and again to see where she get the solve, or you go to math, okay, and then the first option already math, right? Okay, solve happens to be at the very bottom. Happens to be the very bottom. Yeah, sulfur, I guess that's what we have here. Yeah, that's why she said, okay, just go up instead. You see? Okay, if you go up, you then goes to the very bottom right away. Okay. So her calculator is solve. Ours is sulfur. Let's see my program. What did I use? Oh, I have solve here. I wonder why. Maybe it's already updated one. It's the same. It's the same calculator though. Hers is TI-84 plus silver edition. Mine is also. So I don't know. I don't know. I don't know why it's different. Okay, let's start the video again. 1 minus chi-squared CDF. Now, chi-squared CDF is under our distribution list. So it will be 1. Okay, let me make sure you are done with that. Okay, we'll continue, and then it will be minus a comma x comma 0, and then close parenthesis. Okay, that is what will come next. So the difficult part in this line is how to get the display. That's under program, IO, item number 3 display. The solve come from math, and then math, and then at the bottom you will see solve. Okay, and then once you click that solve, then it will start with parentheses. You type 1 minus the chi-square CDF is under our distribution list. Okay, now once you click chi-squared CDF, then it will come with this wizard here. It will guide you. Okay, what is lower bound, upper bound? What is the degree of freedom? Okay, now then After that, let's continue. It will be from here. It will be continue with a minus a comma x comma 0 close parenthesis. Okay, are you okay with this? So once you have that parenthesis, you press enter. It will give you colon again. But if that colon is not followed by anything, then our calculator understands it as the end of the program. Okay, now let's continue. Okay, that's it. So I assume at this point that you already program your calculator, and please do so. Now, if you are using your computer, the emulator, please do not clear your memory. I have a program on my computer that I clear the memory of this calculator. Basically, I clean it up. Don't do so until next week, or basically for the next 1 month. Okay, you can clear the cookies. You can clear. You can clean up your computer in general. Just don't clean up that calculator. Okay, just don't clean up that calculator, because no, it's actually already in the memory of that calculator. It will be safe. Just don't uninstall and install it again. Once you uninstall it, of course, it will disappear. Okay, now, can I assume that you're already done with this programming? If you are, then I go on with 7.3. Okay, which I will do. Now, 7.3. This section, in this section, we will construct confidence interval for population variance. Okay, let's start with the theory behind it, the template or the procedure. To construct confidence interval for population variance is different from the procedures to construct confidence interval for population proportion, and also different from confidence interval for population mean. Okay, it's very, very different. It's very, very different. So in the first maybe 10 minutes, I will explain what are the differences, okay, the procedures and then the assumption. It is because the sample variance S squared is not robust to population variance. Now, what is the word robust mean in here, Thomas? Well, robust means the following, okay? Robust means the following. We say that X bar is robust to population mean. Sample mean is robust to population mean in this following way. Like, because as the sample size increases, the margin of error decreases. Okay, and therefore, X bar, the sample mean, will target the population mean, gets closer and closer to population mean by increasing the sample size. Okay, the error gets smaller. Now, likewise, for sample proportion, it is also robust to population proportion because the sample proportion gets closer and closer to population proportion as the n increases. The larger the sample size, the better you approximate the better the sample proportion approximates the population proportion. That's also because the margin of error decreases. And we can see that in the step 2 of both of them. Yeah, for this guy here, for example, the margin of error is critical value times population standard deviation over square root of n. You see, as n gets larger, you divide by larger number. Therefore, the margin of error is smaller, right? Or if we don't have the population standard deviation, we use the t critical and sample standard deviation, right? Okay, you can see here as the sample size increases and the margin of error decreases. Okay, basically then the confidence interval will get narrower as we increase the sample size. Okay, for population proportion, to construct confidence interval for population proportion, we also have the same situation where the margin of error is critical value times the square root of p hat q hat over n. You see, the larger the sample size, the smaller the margin of error. And therefore, the sample proportion that we had actually estimates gets closer and closer to the actual population proportion. Okay, now that is not the case with sample variance. Okay, that is not the case for sample variance. With sample variance, okay, does not target population variance that well. Okay, it does not target population variance that well. Okay, as maybe I say this way, as n increases, the sample variance may not always may get further away from population variance. Okay, the interval that we get will get smaller, will get narrower as the as n increases, but it doesn't get narrower as fast as the way we did with the previous two confidence interval. Okay, now because of this fact, then the procedure presented here may require a big N. The sample size should be big. Okay, that's one. Now, second thing, another reason, another difference. Okay, secondly, since the sample variance does not target sigma squared that well, the resulting confidence interval for population variance will not have will not be symmetric. Around S squared. So you see, here's the thing. When we did confidence interval for population proportion, the sample proportion is in the middle. You add the margin of error, you subtract the margin of error, right? So the confidence interval you get at the end will have the p hat, the sample proportion, in the middle of that interval. Likewise, confidence interval for population mean. The sample mean is in the middle. You add margin of error, you get the upper bound. You subtract by margin of error, you get the lower bound. Okay, now that is not the case with confidence interval we get later on by using our sample variance as point estimate. In fact, the word point estimate for population variance S squared is not best point estimate for sigma squared. Okay, in fact, some professors even say it's not even point estimate. Now, my standing is, my opinion is, it is still a point estimate, but it is not the best one. Okay, we will use sample variance as point estimate, but we know that's not the best one. Because of the procedure, and you will see the resulting confidence interval we get later on will have the sample variance not right in the middle. It's not right in the middle. It's not right in the middle of the resulting interval. No, it's a bit to the left, maybe a lot to the left. Now the formula later on will be, the upper bound will be n-1, which is the degree of freedom, times sample variance over chi-squared left. That's the upper bound. The lower bound will be the degree of freedom times sample variance over chi-squared right. That will be the formula. Okay, that will be the formula. Now let's write down the procedure, the template then. But pictorially, this is what this is what the confidence interval for sigma squared will look like. Okay, so this is the template now, the procedure. To construct confidence interval for sigma squared. We will find step 1, we'll find chi-squared right. That's the critical value we get from our calculator. That's the program we have earlier. And the second step, chi-squared left. And the third step, first declaration, confidence interval for sigma squared. And then the formula is n-1, which is the degree of freedom, times sample variance over chi-squared right, less than sigma squared, less than n-1 s squared over chi-squared left. Okay, now chi-squared distribution is a non-symmetric, non-negative, skewed to the right distribution. Chi-squared distribution. Chi-squared distribution is first non-negative. Okay, it's non-negative distribution. It's not like our T distribution or sigma or Z distribution. Our T distribution and standard normal distribution is actually symmetric around 0. Okay, and if you have 95 degrees confidence level, then the C score here is the opposite of the C score here. Okay, that's the opposite of the C score there. Now that is not the case for chi-square distribution. Okay, it is skewed to the right, so it's supposed to look like this, right? But the right tail here is being pulled to the right. Okay, now that's a non-negative. Okay, and second, it is skewed to the right. So it is not symmetric. Okay, now later on, when we need to find the critical value, something new we get. Suppose we want to construct a 95% confidence level. Okay, now then we will have this critical value here, which is called chi-squared right, and another critical value here, which is called chi-squared left. Now the remaining 5% is being shared by these two tails. Okay, the remaining 5% will be shared by that two tail. Okay, let's call this the confidence level. It is not in the middle. I should say it is in between, but not right in the middle. Why? Because the shape of these two tails here, this tail and this tail, the area are the same. Okay, both of them has area half of the remaining, right? But the shape are not the same. The shape are not the same. Okay, they are not opposite to each other. Now, the way we program our calculator, then it will be as the following. This is inverse chi. The first number you put in is the area to the right. And then the degree of freedom. Okay, not area to the left. Not area to the left. Now, for chi-square right, it is the area to the right here. That's the area to the right. Okay, now for chi-square left, however, the area to the right will refer to the area from here, the confidence level part, plus the yellow one. Okay? Now you will see as a consequence, later on you see that the area you have here plus the area you have here should total to 1. Okay, it should total to 1. Okay, now let's start with the following example. We will do this procedure and then after that we'll do problem from the book. For example, suppose the sample size is 25, confidence level is 95%. And let's say sample variance to be, let's say 2.7. Construct confidence interval for population variance. So our step 1, will find chi-squared right. This is chi-square distribution. Okay, 95% is the confidence level. That's the area in between. This is chi-squared right, and this is chi-squared left. The remaining 5% is being shared by two tails. So the area of this tail here will be 2.5%. Okay, now then chi-squared right will be inverse chi. The first number is area to the right. Degree of freedom is 24, 1 less than the sample size. Now let's take a look on our calculator, how to punch it in. Oops, uh-oh, what did I do? Exit quick. Uh-oh, did I change the program? No, okay, good. So I call the program first, click program and inverse chi. So you're just barely calling the program right now. You need to enter it again. Now, oops, I did change it. Because the first question is supposed to be area. I did change it. Let me go back quick. Oh, should program inverse chi. No. Edit inverse chi. Yeah, I happen to change it. Okay, let me put it in then. Then that will be input. I go to program, IO, input, and then I'll be alpha log. Where's my colon? Colon is the plus, and then area. It's my R. Area to the right. Colon. Close quote. No, I need to go back. I need to undo the alpha first and then comma. And then A again. Okay. Now quit. Quit again. Let me see the program. Inverse chi. Okay, now I go back to this. So the area to the right 0.025. Degree of freedom is 24. Boom. It's 39,364.08. 39,364. That's 39,364.08. Okay. Now, if you use handheld calculator instead of my emulator, then it may take up to like around 15 to 20 seconds to get this 39.364. Okay. Now, because I use computer, then it runs faster. But if you use a handheld calculator, your calculator may need some time to compute that. And it was around 10 to 15 seconds. It actually depends on the degree of freedom, though. As far as I know, degree of freedom, the higher the degree of freedom, and the longer it will take. Okay, now let's see how about chi-squared left. Chi-squared left will be inverse chi. Area to the right is that 95% plus 2.5%. Is it right? Okay, that will be 0.975. Like what I said earlier, the total you get here should be 1. Okay. Comma, degree of freedom, 24. Now let's put it into calculator. I call that program again. The area to the right is 0.975. Degree of freedom, 24. Now you see that when I press enter, it will take me maybe 1 or 2 seconds only to get it on my computer. If you use handheld calculator, it will take like maybe 10 seconds longer. Okay, this will be 12.40115. 12.40115. Now, then, some technicality. The peak of this chi-square distribution is approximately the degree of freedom. Okay, is approximately degree of freedom. So the number you get here, the chi-squared left and chi-squared right, must be between the degree of freedom. Okay, make sure you have that kind of situation. Otherwise, something is wrong. Okay, the degree of freedom must be between chi-squared left and chi-squared right. So sometimes when I did the grading, I I look at your step 1, step 2. If this is not being satisfied, I don't even need to look at your step 3. Something must be already wrong. Okay, this has to be hold true. This has to be true. Yeah, let me move that here. Now then, let's go on with step 3. Confidence interval for sigma squared is degree of freedom 24 times sample variance, already 2.7. I don't need to square it, it's already the variance, over chi-squared, right? 39.36408, less than sigma squared, less than 24 times 2.7 over 12.40115. Okay, now next we will compute it. That is 1.64617 less than sigma squared less than I get 5.22532. That's the confidence interval for sigma squared. From here, two things. The most common one, sometimes the question actually, sometimes the problem requests or requires confidence interval for sigma instead, the population standard deviation. Now, to do so, you actually just go on one more step from here. Okay, you will do the square root for each side of that inequality, but of course you need to declare again. Okay, you need to declare again. Confidence interval for sigma will be square root of the number on the left less than sigma less than the square root of the number on the right. Okay, and it has to be done this way. It's supposed to be done in two steps. You need to construct confidence interval for sigma squared first, and then after that you construct confidence interval for sigma. Okay, there's a reason behind that though. It has something to do with the fact that while sigma squared, this confidence interval here, we use sample variance to estimate. So sample variance is our point estimate, not the best one, but that's one point estimate. Okay. Remember I said that sample variance does not target population variance that well, right? Now, one of the bad result, quote unquote bad result, is that the sample standard deviation does not target population standard deviation well. In other words, the larger the sample size, maybe result in this situation, the larger the sample size, which is not always the truth. Okay, you need a very, very big sample size for that to happen. Now, the thing is, there have been situations where even if your sample size is very, very large, yet you don't achieve this. Okay, the sample standard deviation does not target population standard deviation well. Okay, that's why when we construct the confidence interval, technically, you need to declare again. Okay, so there's a reason behind it though. There's a reason behind it. Okay, so this becomes a procedure that we're supposed to follow. So this is sigma is less than 2.28590. And this is 1.28303. Okay, so if the question wants you to construct confidence interval for sigma, what you do is just you do square root from each of them. Okay, now one other note, and this is very important note. Important. Confidence interval for P, or maybe for P first. Confidence interval for P requires, so there are requirements that I didn't mention before, I didn't really emphasize that, actually requires that n times p hat times q hat at least 10. Okay, some textbook, they just requires that n times p hat and n times q hat at least 5. Some other textbook. Okay, but the stricter requirement that n p hat q hat is at least 10. Okay, that means the sample size will be at least, like, you should be around, sometimes it's around 1000. It could be also around just around 500. That's also fine. Maybe even 50. Okay, but this requirement is needed so that the distribution of that p hat gets closer to normality. Okay, now for us to construct confidence interval for mu requires either the underlying distribution is approximately normal, or the sample size is at least 30. Basically, you need central limit theorem. Okay. In fact, even if the underlying distribution is approximately symmetric, it's good enough. Okay, as long as your sample size is pretty big. Okay, but even if your underlying distribution is not symmetric, not normal, as long as your sample size is greater than 30, the larger the better, then this model will work. Okay, now the thing is, the confidence interval for sigma squared requires the underlying distribution, the sample where the population, the sample where you get the sample from, okay, the population where you get the sample from has to be normal. Okay, this requirement is strict. This requirement is strict. Okay, the population where you get the sample from has to be normal. Okay, it's not approximately normal, it's not approximately symmetric, it's not because the sample size is more than 30. No. Okay, that's why when we do problems in this section, they need to say, or to be more precise, we need to assume the population where the sample obtained from is normally distributed. Any departure, any deviation, any even if the distribution just slightly not normal, then the model, the procedure we use here is not usable. Okay, now some background, then you will see some background. Because of the strictness of this procedure, most universities do not teach this in their undergrad or in their elementary statistics course, second year course, or first or second year course. They usually teach that in the third or the fourth. You need to know enough stats to confirm, to know how to confirm that a distribution you get it from is strictly normal, not approximately normal. Okay, so that's some background. What happened with our class? We always assume that when we work on this section, we will always assume that the population we get the sample from is normal. Okay, this is the procedure, and that's actually it. This is all we do. This is all we do. Okay, what makes this section a bit difficult? If there's any difficulty, it's on this thing, the first two steps. Okay, you need to have your calculator already programmed, and you know how to get these numbers here. Okay, but the template itself is actually not difficult. In other words, if any students cannot do problems here, either they never exposed to this lesson at all, or even if they see my lecture right now, they don't practice with their own hands. Okay, they never really think about it. Okay, or they don't have their calculator program. Okay, trust me, even though it's only 5 minutes, at most 10 minutes for you to program that into your calculator, that's definitely not something you want to do during your test. Okay, so you make sure you do have this ready for your test next week. It will be in your test. Now, let's go on. Next problem. This time, I want you to try this. Okay, example 2. Suppose the n is, let's say, 37. Okay, and then sample standard deviation is 12. Construct confidence interval, a confidence interval for sigma at, let's say, 97% confidence level. Okay, now let me remind you of the template. The first one, chi-squared right. The second one is chi-squared left. And then after that, you need to do confidence interval, 97% confidence interval for sigma squared. And then after that, you do 97% confidence interval for sigma. Okay. Now, I hope you do it together with me. It's chi-squared distribution. The area in between is 97%. This is my chi-squared right. This is my chi-squared left. The area of this tail here will be half of the remaining 3%. That's 1.5%. Right? So this will be inverse chi, area to the right, 0.015. Degree of freedom is 36. Then you use your calculator. Okay, chi-squared left, it will be inverse chi 0.985. That's 97% plus 1.5%. Degree of freedom 36. Then you get the value from your calculator. Okay, and then the confidence interval for sigma squared will be degree of freedom times sample variance. The one given to us is sample standard deviation, so I have to square it to make it sample variance over the result you get from chi-squared right. Less than sigma squared less than degree of freedom times sample variance over the result you get from chi-squared left. Okay, compute that and then apply the square root. Now, let me ask you to do that. Let me give you 2 or 3 minutes to do this. Okay, let me start. So, chi-squared right, area to the right, 0.015, degree freedom 36. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So it takes approximately 17 counts on my handheld calculator to get this number. That's 56.81138. And then chi-squared left, 0.985, area to the right, degree of freedom 36. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I get 16 counts to get this number on my handheld calculator. Okay, so it's a lot slower compared to if you use the emulator, but I mean, it's only in seconds, not in minutes. Okay, so I will still use my handheld calculator instead of bothering myself with my computer calculator if I have my handheld calculator. Okay, let me go on. This will be then 56.81138. This is 20.11102. Let me compute that. 36 times 12 squared divided by 56.81138. That's 91.24932 less than sigma squared less than 20.11102. At the denominator, I get 257.76912. Now then, confidence interval for population standard deviation will be the square root of those numbers. I get 16.05519. On the right hand side, on the left hand side, I get 9.55245. Okay, you can check your work with mine. Now, once you are done with that, I would like you to do this problem from our textbook. Problem number 9. From our textbook. Dataset 3, body temperatures in Appendix B of our textbook includes a sample of 106 body temperatures, n equals to 106, with mean, so it must be the sample mean, 98.20 degree Fahrenheit, and standard deviation of 0.62 degree Fahrenheit. Okay, now then the question is construct a 95% confidence interval estimate of the standard deviation. Okay, so the confidence level is 95%. Okay, let me ask you to do this. I will give you, let's say 7 minutes to do this. So I will be back at 9:42. Okay, please do that. Okay, let's start again. So solution, step 1, chi-squared right. That's 95% confidence level. 95% in between, the remaining 5% being shared by two tails. So this is 2.5% here. So this will be inverse chi, the area to the right 0.025, degree of freedom 105. Now this will take a while when you use your calculator. While waiting for my calculator, let me start writing chi-squared left equals to inverse chi 0.975, 105. I just get the result here. This is 135.24699. And then I will work on chi-squared left. The area to the right is 0.975, degree freedom 105. While waiting for my calculator, I will start writing for step 3, confidence, 95% confidence interval for sigma squared. That will be degree of freedom 105 times population as that samples variance 0.62 squared over 135.24699 less than sigma squared less than 105 times 0.62 squared over, oh, I get the result already from step 2. That's 78.53640. I don't have a decimal point here, sorry. That's 105, not 10.5. Okay, now let me compute 105 times 0.62 squared divided by 135.24699. That is 0.29843 less than sigma squared less than I get 0.51393. So 95% confidence interval for sigma will be the square root of those. I get the right hand side here 0.71689, while the left hand side I get 0.54629. Okay, Your suggested homework from here, from 7.3, I would like you to do number 5, number 7. We did number 9, number 11, number 13. Okay, 4 question is good enough. Okay, as long as you know the procedure, get used to it, it should be okay. Now, the next section we'll go over today, which is still in your test 3 next week, is Bayes' theorem. In fact, this is the last topic for your test 3. This is the last topic for your test 3, Bayes' theorem. Now, Bayes' theorem is actually the opposite side, the opposite of 7.3. In this sense. I said earlier that most universities, I'm talking about Ivy League included, most universities don't teach confidence interval for sigma squared in their elementary statistic or the equivalent course. Which is strange why we need to teach that. Okay, but because it is in our curriculum, then I teach that anyway. But if you go to UC Berkeley, for example, UCLA, USC, MIT, Harvard, then your professor there, if you transfer from East LA College or West LA College, your professor there will not assume you have learned this. Okay, now why I want to say it's kind of strange, because universities usually usually teach A, B, C, D, E, and in college we tend to teach less than that. Let's say we tend to teach A, B, C, D only, for example. Okay, even though in our syllabus we still put the E just so that our course can transfer, but in reality we don't go that far. And to tell you the truth, sometimes in university level, it's in their syllabus, but they don't go that far either. Okay, but most of the time they do. Okay, usually this is the case, right? Now notice that in this situation, we are actually teaching something they don't require. Okay, that's the case for confidence interval for sigma squared. On the other hand, Bayes' theorem is like the E part that university level usually require you to already know. So when you go to university later on and you need to do some kind of statistical analysis, your professors will assume you know Bayes' theorem. Okay, and strangely, it is not required in our curriculum. Now, our textbook is written for college students. Okay, most of the time. In university, they usually don't use Triola. Okay, therefore, our textbook does not have Bayes' theorem explicitly. Okay, but why do I teach this while it is not in our curriculum? Because when you transfer to university later on, your professor will assume you already know this. And Bayes' theorem is actually very, very useful in our daily life too. And that's why I want to go over this also. Okay, very, very useful. Trust me. For me personally, I have used Bayes' theorem at least 3 times in very important instances of my life. At least 3 times. And one of them, actually, I should say 4 then. One of them, I applied that approximately last month. No, I should not say last month. Is it last month? Yeah, last month. When I get my second vaccine. When I get my vaccine, I originally thought that it's not worth it for me to get the COVID-19 vaccine. Okay, and I used this Bayes' theorem. Okay, I will show you later on my computation. Okay, and then my eye doctor was the one changing my mind. Okay, yeah, let me explain to you first what is Bayes' theorem. Bayes' theorem is a theorem that provides the following informations. Okay, they give us probability of A and the probability of B given A, probability of not A, and probability of B given not A. With those given informations, they want us to find probability of A given B. Okay, this is very theoretical. And the formula is probability of A given B is equal to probability of A times probability of B given A divided by, I copy paste what I have on the top, plus probability of not A times probability of B given not A. Now, the way I learned it before, when I was at university, when I learned this Bayes theorem before, was basically exactly like this. And I tell you what, nobody likes it. It's like everybody didn't care. And this was the last section of that chapter, so nobody really studied, including me. You know, why? You give me formula and I don't know what's that, you know, and my professor just keep on talking. And I didn't study, my friends didn't study. But as usual, the next day we met, my professor gave us little quiz. Of course, we bomb it, right? And the next time we met again, it turns out that my professor asked similar question again, Bayes theorem, because we didn't do well in that Bayes theorem quiz. So she quizzed us again and again and again and again. So after 3 times, she figured out that we didn't really study Bayes theorem. So she said that, hey, you know what? Seems like all of you don't care about this. I will keep on asking about Bayes theorem until you study that. Okay, and trust me, my next test will be all Bayes theorems if you still don't get it until that time, because of her her threat. So we end up studying. Okay, we as usual we have group study, and later on we realize, hey, you know what? It's really the way she presented it. Okay, no, don't get me wrong. This professor is someone I really look up to. Okay, now, and her assumption is she wrote the formula on the board, and we will actually look deeper into it during our study at home, which we didn't do. Okay, so it's not her fault. She has her assumption, which, I mean, she has had that assumption even for other cases. She gave us this framework, and then she wanted us to study at home to dig deeper into it, which we didn't do. Okay, so then later on we realized, you know what? After we study for a while, then we realized, you know what? It's really about the way we present. We need to present this Bayes theorem in more basic approach. Okay, her assumption is correct though, because she was teaching in math department, so she did assume that our math background is already strong. Okay, now we were just lazy. However, I do not assume the same background with you. You are not a math student. Okay, so it is more appropriate if I don't start with this formula, I will start with a procedure instead. Okay, now let me do the following. Okay, how do we apply Bayes theorem? Let's say, for example, okay, in a population, okay, let's say 54% are women, and of course the rest are assumed to be men. Okay, now in a population, 54% are women, the rest are men. Now, let's say 40% of women, and let's say 37% of men wear glasses. Please keep in mind that whatever topic I discuss in this class, not only discuss, but for my whole semester, whatever topic I discuss throughout my whole semester does not reflect or does not reflect my personal view, and there's no intention whatsoever to tell you what to believe, what not to believe. Just take it at the statistic level, okay? Now, it's not that, oh, you know what, Thomas, why you pinpoint people wearing glasses? Like you don't like people wearing glasses? No, it doesn't imply that way at all. I myself wearing glasses, okay? I myself wear glasses, okay? So it's not about you wearing glasses or not, okay? That's what I meant. That's what I meant. So simply because we talk about that doesn't mean I'm against or I'm supporting something, okay? Later on, we may talk about COVID, about vaccine, about wearing masks. I am not in position to to tell you that you need to get your COVID vaccine. In fact, I told you earlier that I originally did not want to, did not have the interest to get the vaccine until my eye doctor actually changed my computation with a new information that I was not. I was aware of that, but I didn't really think about that far. Okay, so me personally, I need to take COVID-19 vaccine. Okay, but how about you? It's on your. It's you consider it yourself. Okay, I still believe in personal responsibility and therefore personal choice, personal right. Okay, that's what I believe. Okay, so it's up to you if you don't want to take your COVID-19, you know. But if something happened to you later on, you know, that's the consequence of your choice, right? I mean, and I still respect that, and I still respect that. Okay, I will not say, oh, told you you're supposed to have taken your COVID-19. That's no, it's like, hey, you choose not to take it if you get the consequence, and if I can help, I still help. Okay, I will not say it's like it's because you didn't take the vaccine and therefore right now I don't want to help you. No, I still help you. Okay, no, I'm not that kind of person. In fact, I want you to realize that my view on mask, for example. Okay, I'm not someone who will in like force other people to wear mask. Like, hey, you know what? You are in public. You will wear your mask. I'm not the government. Okay, I'm not saying that government is wrong to enforce that. No, I'm saying that as a regular citizen, I'm not in place to force you to do that. Okay, my choice is like if I see you choose not to wear your mask and I don't feel comfortable with you, what do? I walk away. Okay, I walk away. I'm not telling you to go away. No, I'm the one. If hey, you know what? If you don't feel comfortable with me, you walk away. If I don't feel comfortable with you, I walk away. Okay, not that I don't feel comfortable with you, then I need to push you away. Nah, that's not me. Okay, that's not me. If even if you choose to have that kind of stand, it's up to you. Okay. The only authority I have on you is when it comes to statistic in this curriculum, in what I teach. Okay. Other than that, hey, you know what? We are just regular citizen, regular resident, right? Okay. Yeah, my position and your position in the society are exactly the same. Okay, I have no more right than you to tell you what to do, and just like you have no more right to on me what to tell me. Okay, oh, of course, opinion will be appreciated, right? Okay, and I will show you my computation later on why I first decided not to get the COVID-19 vaccine, and then later on why I changed my mind. Okay, so I'm not someone who's like, hey, you know what, after I make up my mind, I will not change because I believe so much into my science. No, some extra information will be useful. Okay, now suppose we have this situation. Okay, and the question is, of those wearing glasses, what proportion are women? Okay, now let's formalize this first. the population proportion of women or probability a randomly selected person is a woman is 54%. Probability of men, therefore, for sake of simplicity again, for sake of simplicity in my class, we will just use binary, gender, women and men. In public, you may think it's actually a spectrum. Okay, it's not men, women, binary, maybe others. Okay, it's a spectrum. Yeah, it's a spectrum. So men will be 1 minus 0.54, that's 0.46. Now, what is that? 40% of women wear glasses. What is that? So given that person is a woman, the probability that person wear glasses is 0.4. Given that person is a man, the probability that person wear glasses is 0.37. Okay, that's the information. Now, to answer this question, we will break it into 4 steps. Okay, the first step is we will construct the probability tree. We'll construct the probability tree. Now, just like you see in my lecture, my videos, like every time you construct a probability tree, okay, the event is written at the end of the branch. The probability is written, or the proportion is written on the branch. Okay, and every time you have branching, the total should be 100%, or in decimal that will be 1. Let me make it in percentage. So this is 54% and this is 46%. Now of women, 40% of them wear glasses. And therefore 60% not. Of men, 37% wear glasses. And again, the numbers I use in this course, not only for today, but in this course in general, are hypothetical. Okay, hypothetical. Don't take it as face value. This will be 63%. I mean, I just randomly pick numbers. How you get that 37%, Thomas? Did you do any survey? No, no, I just randomly pick numbers. Okay, I just make up numbers. It's hypothetical. Okay, the purpose is not to come up with a conclusion that you will apply in your life, but you come up with a procedure that you can apply in other cases. Okay, now part B, we will find the proportion or the probability a randomly selected woman, a randomly selected person is a woman and wear glasses. Okay, and that will be woman times glasses. Okay, that will be 54%. It has to be a woman first, and then knowing that person is a woman, that person wear glasses. Okay, now never multiply percentage with percentage, never. Change them to decimal first and then multiply in decimal. Okay, then change it back to percentage if you want, but that's okay. We can just leave it like that. Okay, How about if we want to find the probability a randomly selected person is a man and wearing glasses? Man and wearing glasses will be this one, right? That path. So 46%, that's the probability of selecting a man, and 37% of getting a man who is wearing glasses. 37% probability of wearing glasses from that man. Change it to decimal. I get 0.1702. Okay, now that's for part B. Part C. Then we can compute now the probability that randomly selected person actually wearing glasses. Now, either that person is a woman and wearing glasses or a man wearing glasses, which we have computed in part B. That's 0.2160 plus 0.1702. Okay, for a person wearing glasses, either that person is a man or either that person or a woman, which we have computed in part B. And I get 0.3862. This is the proportion of the whole population wearing glasses. Now then, lastly, what is the probability? What is the probability that person is a woman knowing that person wearing glasses? Given that person is wearing glasses, what is the probability that person is a woman? Now, this is the kind of analysis you may want to do if, for example, you open an optometrist, like you hire an optometrist and then at the front of that store, you actually sell glasses. Okay, and that's actually the common setup, right? Do you realize that when you go to optometrists, most of the time they sell glasses? Okay, now the thing is, like, if you are the manager, okay, if you are the manager, you want to sell glasses, okay, then your glasses supposed to be most of them for women or most of them for men. Of course, you need to serve both, right? If you are selling glasses, okay, but will you sell will you have more models for men or more model for women? Okay, what will your target market be? Your priority. Okay, so you see that these informations that you think like it has meaningless, right? Okay, suddenly becomes something you want to know for your business decision. Okay, to better target your audience, right? Okay, I'm not saying that because later on this will be mostly women, then you will target your market for women. No, in fact, one thing you will see later on that when I get my new glasses, in that optometrist, all the frames, most of them are actually for women. And I was just like, hey, do you have other ones for men? Oh, you know what? Men usually just use this one. It's like they already stereotype the men one. No, not in this way that I get offended. No. It's just like, hey, you know what? I want something that quite special. I don't like my glasses with frame. I like my glasses to be small size and without frame. Okay, it's just like, how to say that? It's how to say, it's not, the frame is like as minimum as possible. I'm some kind of a person who is minimalist. So I try to live with less items in my life. Okay, that's my personal choice though. Okay, so when I look at those choices for guys, it's just like, no, these are a lot of them with branded one, expensive, and no, that's not what I want. I want something simple, small. I don't really mind with the price, but it's just like, hey, do you have other choice? And I keep on asking them that, you know. Yeah, and that's please realize that's actually a market also. Okay, that their impression is like most women are the one want some style, which I agree more or less, but it doesn't mean no guys need some style. I have my own style too. Well, anyway, then what end up happening is I get my old frames and ask them to put the glasses on that. Well, anyway, at this point, then we can compute this probability of selecting a woman knowing that person wear glasses is probability women and wear glasses, which we already get in part B, over probability somebody wear glasses, which you get in part C. Okay, this will be 0.2160 over 0.3862. Okay, 0.2160 over 0.3862. That's 0.55930. So approximately 55.9% of those wearing glasses are women. And to say even more, of course, I would like my wife to be not modest, but of course, it's up to her. But I will give her freedom. She has the right to access the money anyway. But if she asks me, I will say, you know what? I want you to have more choices. If necessary, you get 2 frames instead of only 1 frame, so that you look nice when you go out, yet at home you can wear something simple. You see what I mean? Okay, so I want her to have more choices too, not only me. Okay, when it comes to money, hey, you know what? I need to make her happy, right? I need to make her happy. Yeah, I'm the one working at home, but she's also working at home taking care of my kids. Okay, it just happened that it doesn't show up on her paycheck, right? But doesn't mean she didn't work. Okay, I appreciate her for what she does to me and especially for our children. Okay, so now we finish this question. What is the probability or the proportion that of those wearing glasses, they are women? Okay, I tried to put some flavor into this question, like how it will impact us in making decision if this is a business decision. Okay, so originally the question seems to be very innocent, quote unquote, like, hey, you know what? What's the point of me knowing this? But once you put some flavor into that, like, hey, you know what? You will hire an optometrist to work for you. Let's say, for example, or let's say your daughter, your son is an optometrist. Okay, and you want to give them some capital to have their own clinic. Okay, and of course, if you are an optometrist, you would like to have also provided the glasses, right? Okay, and one of the thing that you want to sell is the frame. Then how will you manage your store? Yeah, like that. Okay, now let's see the next one, the next example. This time I will take it from my, give me a second, from here. Let me ask you to do this. Let's call this your example 2. A computer manufacturer has its chips supplied by supplier A and B. Supplier A provides 65% of chips, and supplier B provides the rest. Of those chips from supplier A, 2% of them are defective, and of those from supplier B, 3% are defective. Now, part A construct the tree diagram. So it's either from A or from B. Is it right? 65% from A. The rest, which is 35%, of course, is from B. Now, of those from A, 2% of them defect. Now, it's not that they purposely give us something defective. No. Sometimes, actually, most of the time, it's because they don't even know that after they produce that, they test it, it works, but somewhere in between, maybe the way they store it, the way they transport it to you, or maybe the way you receive the package from them, make it defective. Okay, something can go wrong in between. Okay, so that's 98% being good, while the one from B, 3% defective, and therefore 97% are good. Okay, now that's the tree diagram. Part B. Part B, find the probability that a randomly selected chip is defective. To be defective, it has to go through this path or this path. Right? Okay, so to be defective, probability of defective, it's either from A and defect or from B and defect. This is A and defect plus B and defect. Now change them to decimal first. Again, don't attack them right away from the percentage. This will be 0.0130 plus 0.0105. So the probability that a randomly selected computer chip is defective is 0.0235. So if you actually pull those chips from A and B together, then that mixture will have 2.35% of them defective. Okay, now part C. Find the probability that a defective chip is from supplier B. Probability that it is from B given that's defective. That will be probability of D intersection over probability that it is defect. The intersection is 0.0105. That's why I do not recommend you to compute this right away and get this. No, I don't recommend you. So, okay, because you're supposed to compute one by one. Get this first and then get this and then add this. Otherwise, you don't have this number to use in your next step. Okay? Over 0.0235, which will be 0.44681. That's the probability that a defective chip is from supplier B. Okay, now please leave some space before example 3. I will give you a follow-up question here later on. Give some space. I will give you a break together with the following question. Yeah, leave some space. We will have part D later on. Let's do the next example. This is example 3. Oh, way too big. 46% of US population are male. So you know what percentage is female. Okay, and suppose 5% of all male, 0.4% of women are colorblind. And first, construct the tree diagram. Second, probability that a person is colorblind. And probability a colorblind person is a female. Okay, now let me ask you to do this problem together with your break. This problem should take you, it's supposed to be only around 5 minutes though. But let me give you 7 minutes together with your break. We come back at 10:40. Okay. We come back at 10:40. We're done, and you are done with all these three parts at that time. Part A. 46% of your US population are male. So 46% male. Then 54% female. Now then 5% of all male colorblind. And 0.4% of female are colorblind. Let me use CB instead for colorblind. 0.4%. So the one not colorblind of men, 95% of men not colorblind, and of women not colorblind, 99.6% not colorblind. Now, then part B, what is the probability a randomly selected person is colorblind? That is equals to probability men and colorblind plus probability women and colorblind. That is 46% times 5% plus 54% times 0.4%. That's 0.46 times 0.05 plus 0.54 times 0.004. That's 0.0230. Plus, this one is even more. That's 0.00216. So put them together, that will be 0.02516. Is it right? So the proportion of colorblind people in our society is 2.5%. I try to get this number as close as possible. As I remember, I get this from from some journal, from some report. So this number, I think, is close enough to the actuality. Okay, but now that's not the purpose though. The purpose is really to apply, just to apply statistic. Okay, now part C, what is the probability that a colorblind person is female? So given that person is colorblind, what is the probability that person is a female? That is equals to probability female and colorblind over probability of colorblind. That is 0.00216 over 0.02516. I get 0.08585. So approximately 8.6% of those colorblind are women. Okay, now let me go on a bit more. Remember I said that I have follow-up question. Now let's see part D from here. Part D. Of 40% colorblind persons, find the probability at least 30 of them are male. Oh, hold on. There are 40 colorblind. Okay, what is the probability it's a male given that person is colorblind? Well, it will be female given that given that person is colorblind, probability that is female is this. So the probability that that colorblind person is a male will be 1 minus 0.08585. Okay, that is 0.91415. Now, of course, you can also do it long ways. You can say probability, that's the first alternative. The second alternative, probability of male and colorblind over probability of colorblind, right? That's 0.0230. That's the number we get from part B over 0.02516, also the number we get from part B. Okay, now then coming back to the main story. Now let X be number of males in 40 colorblind persons. Then this X will be binomially distributed, right? It's either male or not male, right? Okay, they are colorblind. It's just the question here, are they male or not male? Okay, so there are 40 trials. Probability for being a male is 0.91415. What is the probability that at least 30 of them are male? That's 1 minus probability that X is at most 29, right? That is 1 minus probability. Oh, that's no binom CDF. That's binom CDF. Trials 40, probability of success 0.91415 up to 29. And I compute that. Binom CDF, number of trials 40, probability of success 91415. We need up to 29 males. That will be 0.00041. Oh, wow. So it will be 0.99959. So almost sure that we have at least 30 of them male. Okay. By the way, one of my best friend, best friend, later on I found out to be colorblind. He himself actually didn't realize he was a colorblind until he was in his second year. So he was 19 years old when he realized that he is colorblind. Yeah, well, I mean, we live in the same apartment for 2 years when we realized that, hey, you know what, that's green, and he said, no, that's blue. And later on, we found out that he cannot differentiate a blue and the green. Oh, the blue is greenish and the green is bluish. I have to agree. Okay. And now let's go back to example 2. I told you earlier that I want you to skip a little bit. That's because there's a follow-up question I would like you to think about there, similar to the one we did just now. Part D. Of 25 defective chips. So knowing that these chips are defective, what is the probability that more than half of them from supplier B? Probability that it is from B knowing is defective is 0.44681. Now let me start here. Yeah, well, here. Let X be number of defective chips from B. Then X will be binomially distributed, 25 trials. Probability of each defective chips to be from B is 0.44681. Now the one in question is find the probability that more than half. More than half of 25 means more than 12.5, right? Starting from 13. Therefore, the complement will be up to 12. So this is 1 minus binom CDF 25, 0.44681 up to 12. Use my calculator. 25 is the number of trials, 0.44681, the probability that each a defective chip to be from B, and then we need up to 12 of them. That's 0.70498. So the probability will be 0.29502. Okay. Now that's for our base theorem. The application is actually far-reaching. If you take a look on the handout I gave you last week, consider that as your suggested homework. Okay, it's not in our textbook, unfortunately. That's why I need to give you that handout to study from. Okay, from last week. Okay. Now what I will do next is I will go over all tests. This time I will take it from spring. Is it spring 20? Give me a second. Which one I said that I will go over? Let me look at my, yeah, I will go over spring 21, the one from spring 20. So exactly last year. Yeah, make sure you study the one from fall 20 though. Okay, make sure you study the one from fall 20. I provide you the solution there. Okay, I provide you the solution there on the discussion board. Okay, make sure you study from there. Let's see the view, make it 125% view. Now, some students usually ask me this question, Thomas, do you provide extra credit, like a new assignment? No, I don't provide such extra credit. During my test, in my test, I may give you extra credit. But outside of whatever I said in my syllabus, I'm not supposed to give anything more. Okay. And we are not supposed to start thinking how to do well and after we don't do well, right? In other words, from the beginning, start thinking about that. Okay, like working hard since the beginning. Don't wait until you don't do well, then think about, oh, there must be some extra credit. No, no, you're the one not doing well. Why do I'm the one supposed to do more grading? Huh? Oh, okay, but I do give extra points at that time. But this was spring 20. So at that time, even students are still adjusting to how to study remotely, right? Okay, in my fall 20, the one I show you here, in my fall 20, if you take a look, the in-class test was 100 points. The supplement is 110, is 10 points, or total of 110. Now, I do not expect, however, your test will be more than 107 points, however. Okay, 107. I don't think it's more than 107. Okay, especially because I already go over spring 20 with you, and I provide you the solution for fall 20. Okay, now let's take a look. Test 3 from spring 20. I will use blue color solution. Oops, what happened? How many pages here? Huh? Huh? Doesn't say how many pages. Okay, well, I think that's 7 pages. Now, later on, I will provide you the solutions. Most students think that the written solution is actually good enough, but the reason I go over it in video is because there are some students may get help. And of course, you can ask me question directly when I go over that in class if you have question. Now, students who don't attend the class directly live with me, of course, basically waive their right to ask question directly when that question arises. Okay, so feel free to interrupt me if you have question. Okay. Now, number 1, weights of bags of goodie cookies has normal distribution with a mean 16.2 ounce and standard deviation 0.8. A box contains 12 bags. So let X be the weight of a goodie cookie bag. Okay, that's a bag. This X is normally distributed with mean 16.2, standard deviation 0.8, so I square it for variance. Now, part A, find the probability that a bag of goodie cookie X is less than 16 ounce. Less than 16 ounce. That's normal CDF. Negative E, 99. Up to 16. The mean 16.2, standard deviation 0.8. That is equal to, so always write the probability notation and then the calculator notation, then the calculator result. I get 0.40129. Okay, that's for number one. And you can see here, even though it seems like a lot of, I give you a big space, that's because some students still learning to write on files or on paper that they print at home. Basically, it makes you feel that the test is long, but you see, that's because I give you a lot of space, right? I don't want you to feel crowded also. Part B, 95% of all bags weigh more than K ounce. Find K. So if this is our normal distribution, the mean is 16.2. What is K such that the area to the right of that is 95%? Okay, now don't forget, we start from probability notation. Probability X is greater than K is 95%. Now we will use inverse norm, but inverse norm only works if you have the area to the left. Okay, so let's change this. If the area to the right is 95%, then the area to the left is 100% minus that, right? So 1 minus 0.95, that's 0.05. Now then from there, the K is inverse norm, 0.05. The mean is 16.2, standard deviation 0.8. I get 14.88412 ounce. Okay, that's for part B. That's for part B. Part C. A box which contains 12 bags is selected at random. Find the probability that the weight of that box is more than 200 ounces. And the hint is consider the average. So probability that the box, the weight of the box is more than 200 ounces. But that means the average weight of those 12 boxes is more than 200 over 12, right? One box consists of 12 bags, means the average of those 12 bags must be more than 200 over 12. Okay, now x bar 12, the x is already normal, so by central limit theorem, the sampling distribution will have normal distribution already with the same mean, yet the variance is the original variance divided by 12. So the probability that the sample average is more than 200 over 12 will be normal CDF. The lower bound 200 over 12, upper bound E99. The mean is 16.2. The standard error is 0.8 over square root of 12. Then use your calculator. Again, this is equals to 0.02165. A very small probability. A very small probability that the average is more than 200 over 12, and therefore the box is more than 200 ounce. It's possible, but the probability is small, 2%, 2% something. It's not so small either that we will say, oh, it's next to impossible. No, it is still possible. Let's say if you have 1,000 boxes, 1,000 such boxes, then you may expect 21 or 22 of them have that characteristic. So it's not that it won't happen. Okay, it may happen. That's something I will not bet on it. Okay, unless I have the price is good. Okay, part D, a box which is 12 bags is selected at random. Find the probability that at least half of the 12 bags weigh more than 16 ounces. So this is not about the weight anymore. This is the number of bags with that characteristic. So let Y be number of bags weigh more than 16 ounce. Now this Y will be either it weigh more than 16 ounce or not, right? So you have 12 bags. The probability that it weigh more than 16 ounce, something we did in part A. Oh, actually, no, that one is less than 16. So to be more than 16 will be, I need to see the number up there. Let me see. Yeah, to be less than 16 is 0.4 something. So to be more than 16 will be 1 minus 0.40129. Right? Okay, let me write a note there. This is the probability that x is less than 16. So this will be probability that x is more than 16. Okay, the complement, right? Now then, y, find the probability that y is at least half is more than 6 of that 12, right? More than at least 6. But this is equals to 1 minus binom, 1 minus probability that y is at most 5. That is 1 minus binom CDF 12 trials, probability of each success. You can compute that first, but I'm lazy, so I will just put that as is. Up to 5. Twelve, 12 is the number of trials. The probability of success is 1 minus 0.40129. Up to 5 successes. That's 1 minus 0.16050. So 1 minus that will be 0.83950. That's the probability that at least half, probability at least half of them, of these 12 bags weigh more than 16. Okay. I'm sorry. That's for part D. Let's go on with part E. Continue from number 1, where the information is that a bag has normal distribution with mean 16.2 ounce, standard deviation 0.8. A box contains 12 bags. Now, what if the average weight of 12 bags is at the bottom 10%? At the bottom 10%. So you have a normal distribution for that sample mean distribution. And the average of that is at the bottom 10%. The question is, what is this here? What is the maximum average weight, K, does those 12 bags have? So probability that x bar 12 less than k is 10%. Find k. That will be inverse norm. The area to the left 0.1. The mean is 16.2. The standard error 0.8 over square root of 12. Okay, don't forget that x bar 12 is normal with mean, the same mean with the original population, but the error, the variance will be the original variance divided by 12. Therefore, the standard error will be the square root of that variance. Using calculator now. So K is 15.90404 ounce. Part F. A consumer advocacy inspector will take a random sample of 10 boxes. So 10 boxes implies you have 10 times 12 bags, right? Okay, and sue the company if the average weight of these boxes is under the weight claim on the label of the boxes. So you have a box, okay, and that box says content 12 bags, right? Now, but how about the weight for this box? Let's call that weight is K. Okay, now, if the company is willing to run the risk of being fined 2% of the time, with what weight should it label its boxes? So what is that K? How will you label the box such that you only have 2% chance of being fined, being penalized, because it turns out that your boxes are underweight? Okay? So here's the thing. The probability that the total weight of 120 bags is less than K is equal to the probability that the average weight of this 120 bags is K over 120. Is it right? Now you want that to be less than 2%. Equals to 2%. So K over 120 is inverse norm 0.02. The mean is 16.2. The standard error, however, is 0.8 over square root of 120. So I get K over 120 is equals to 16.050015. You can make it 2 if you want. 002. So K equals to 120 times that. Okay, so that will be 100. Oh, hold on. This is for, oh, okay, this is, the total should be 1,926.001846 ounces. But this is the weight for 10 boxes, right? That's the weight for 10 boxes. That's the weight for 10 boxes. So the K here is not the K that I meant earlier. You know what? I want to fix something. So the total weight of 10 boxes is less than 10K. So this is 10 here. This is 10 here. This is 10 here. This is 10 here. So K itself will be divided by 10. 192.60018 ounce. Okay, because per box we call that K, right? So 10 boxes, the weight should be less than 10K. That's for part F. Let's go on with number 2. We did this just now. A computer manufacturer has its chips supplied by supplier A and B. Now, after testing the chips, 7% of them defect. Oh, okay, so the branching is first defect. So 7% defect. It means 93% is good, right? Furthermore, 45% of the defective chips and 40% of effective chips are from A. So of those defects, 45% of them from A. Of those good, effective one, 40% from A. Now, and then of course, the remaining from B, right? So 55% of those defects from B and 60% of those good from B. Now then part B, question B, find the probability that a randomly selected chips is from supplier A. Probability that it is from A must be through this branch plus through this branch. Okay, that is probability that defect N from A plus probability that it's good N from A. That's 7% times 45% plus 93% times 40%. Okay, 7%, that's 0.07 times 0.45 plus 0.93 times 0.40. That will be 0.07 times 0.45. That's 0.0315 plus 0.93 times 0.4. That's 0.372. I get this is 0.4035. So A actually supplies around 40% of the chips. That's for part B. Now let's see part C. Find the probability that a chip from B is defective. Given that it is from B, what is the probability that it is defective? That is equals to probability it is from B and defect over probability it is from B, right? Probability it is from B and defect, if you look at the probability tree, it has to be defect and B. This guy and then this guy. Is right? This is for A. I color it that way. And for B, I mean for part C, I color it this way. Okay. A probability that it's from B and defect, that's 7% times 55%. 7% times 55%. Now, how about probability it is coming from B? Now, you can do the computation that we did in part B earlier, similar to that one, or thinking this way. Well, the chips, it's either A from A or from B, is it right? The chips is either from A or from B. Now, if from A 0.4035, then the probability it is from B will be 1 minus that. You see that? Okay, so that's 1 minus probability of A, 0.4035. So this will be 0.07 times 0.55 over 0.5965. That is 0.06454. 0.06454. Part D. Of 100 chips from B, so that's the n equals to 100, find the probability that more than half of them are defective. Probability that it is defective, knowing that it is from B, is actually very small, 0.06454, right? Okay, now let X be number of defective chips from B. Okay, so this X will be binomially distributed. The number of trials is 100 chips. The probability that each one of them is defective is 0.06454. So probability that the number of defective chips is more than half, that's more than 50, is 1 minus probability that X is at most 50. Now, this is binomial distribution, not normal. If it is normal distribution, you can just use normal CDF 50, E99, blah, 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 right? But because this is binomial, then the cumulative is only up to a certain number, not from a certain number. That's 1 minus binom CDF 100, 0.06454, 50. I get 1. So the probability that more than half are actually defective is practically 0. No, there's no chance. We do expect some defect, right? But you don't expect more than half of them defect. Yeah, you don't expect half of them, more than half of them defect. Part E is the new question that you don't see from my old test. Oh, by the way, I give you 2 old tests to study from. Why nobody interrupt me? No, why nobody interrupt me? Why nobody interrupt me? I keep on talking about. Oh, man. Well, anyway. Nobody interrupt me. Okay, fine. So earlier the view was from, yeah, I keep on talking about that. Well, later on you print this out then. Okay. Okay, so number 1 and number 2. Number 1 EF. I am working on number 2 right now. Okay, you look at the solution. Too bad nobody interrupt me, so you don't see that my screen was still at the my screen was still at the discussion board. Well, anyway, part E is basically a new question that I never showed before. Basically, can you convert the probability tree that you had earlier now to contingency table? We have 2 types of branching. The first branching about effective or defect. The second branching from A or B. Okay, now we know 7% are defect, right? So this is 7% here. The effective one is therefore 93%. Okay, from part B, we found out that 40.35% actually from A. In fact, we can go further. The defect and from A is here, right? Good and from A is this one. Okay, I will put those numbers in. What did I do? So this will be 3.15%, and this will be 37.2%. Okay, now to get the B's, the total B here, you just subtract that from 100, right? Which we actually also computed earlier here. This is 59.65%. So that's why from your ABCD, if you show work properly, then what you do here is supposed to be just looking at what you have done earlier. Okay, it's just about you organize your informations. And this guy here, 7% minus 3.15, that's 3.85%. This guy here will be the one add up to that. So I will do 59.65 minus 3.85. That is 55.8%. Yeah, of course, you can also do 93 minus 37.2. You will get the same result. Okay, now that's for question number 2E. Again, earlier my screen was at the discussion board. So basically, all questions from number 1 was not properly feasible, but I will post this solution later on the discussion board, right? So at least you have something in writing, not in video. For number 2, most of them not in video, but at least you still have in writing. Okay, good thing I checked before I finish this, that part E, we still can see the video. Okay, let me go on with question number 3. The number of times a math student seeks tutoring from Math Center in a week is a random variable x with the following distribution. The total should be 1. right? So I will do, to find this, I need to do 1 minus the total. Okay, that is 1 minus 0 0.6, 0 0.95. That's 0 0.05. Okay. Now, part A. Find the average number of times a math student seeks tutoring from Math Center on average in a 1-week period. Extend the table above, then provide your result below. Make sure you use correct notation. So to find the mean, I multiply p times x. This is 0, 0 0.25, 0 0.40, 0 0.45, 0 0.20. I get 1.3. So the expected number of times a math student seek tutoring from Math Center will be 1.3. Okay, you need to write the number, of course, and also the notation. The notation you use may be expected EX, or you can use mu sub X, or you can simply just use mu, not X bar. Okay, you need to give me the correct notation. Now, part B, find the standard deviation of times a math student seek tutoring from Math Center in a 1-week period. Extend the table above, then provide your result below. Make sure you use correct notation. So actually standard deviation, then I need to do x squared, huh? X squared, px squared. That's 0, 1, 4, 9, 16. That's the x squared multiplied by the probability. Then I add those. Let me use my calculator. Huh? Okay, I'm sorry. I punched something wrong. I get 3.2. So the variance will be the variance of that random variable x. You can also write sigma squared x. You can also simply write sigma squared is 3.2 minus the average squared. Okay. You know what? Let me write it. I don't want you to think that you need to write all 3 of them. No, you just need to write one of them. Now the notes here is that you can write var parentheses x or sigma subscript x squared or sigma squared. Now, of course, preferably the one with identification for x. But we are not done with this question because the question is to find the standard deviation. What we got here is the variance. So the standard deviation is the square root of 1.51. That is 1.22882. Okay. By the way, the notation for standard deviation, it's either this guy or this guy. Okay, or simply sigma. SDX is not a widely acceptable notation for standard deviation, so we will not accept that here. Now, part C. Find the probability that 100 math students will seek tutoring from Math Center in a total of 180 times or fewer in a week. Okay, the probability that the total times 100 math students will seek tutoring from Math Center to be 180 times or fewer. So the total is less than equals to 180. If the total is less than equals to 180, means the average of these 100 students will be at most 180 over 100. Is it right? Now, here's what happened. The x is not normally distributed. The x, we have only the mu is 1.3 and the variance 1.51, right? But by central limit theorem, because the sample size is far above 30, then the sampling distribution of that 100 will becomes normal, with mean the same, variance, the original variance, divided by square root of the sample size. Okay, so suddenly you can use central limit theorem, which you could not earlier. This will be equals to normal CDF negative E 99 up to 180 over 100. The mean is 1.3. The standard error is square root of 1.51 over square root of 100. I'm sorry, I should not use square root here. Yeah, just 100. Okay, now you can replace this square root of 151 here with the number you already have in part B, 1.22882. That's normal CDF, negative infinity up to 180 over 100. The mean is 1.3. The standard error is square root of 1.51 divided by 100 under square root. So I get this is 0.999976. So the probability is actually very high, almost sure that the total number of times they, how to say, it's almost sure that they will seek at most 180 times tutoring. So imagine if one student, every time a math student go to the math center and request tutoring, let's say they will get 1 hour time slot. Then what is the probability that these 100 students will require at most 180 hours? And the probability will be almost 1, that they will need at most 180 hours. Now that will help the math center to compute how many tutors they need, right? Of course, we're supposed to break it even further. There are busy times in the tutoring center. There are times that's not as busy. Okay, but from there we see that, hey, you know what? The manager or the director of Math Center can then decide during what time we need to have how many tutors, during what time we have less. Okay, and how many tutors we need to hire. Okay, so you see, this probability thingy is then being used to compute the need. Of course, we cannot be 100% sure that it will be at most 180. I mean, if you want to be 100% sure, then you need to get like infinite number of tutors. But that's not in line to the amount of budget we have, right? In fact, the budget we have at Math Center, just like in other places, the Math Center will be assigned, will be provided some budget, and using that budget, the manager will be the one in his wisdom, based on his or her background in statistics, compute how to manage this money and therefore do the related hiring of tutors. Okay, now imagine if this is the case in a store. Okay, yeah, using this ability, then you can actually allocate the money from your budget more wisely. And trust me, then your employees will also be happier because they don't get too busy, right? Of course, everybody wants to be busy, right? Okay, especially during this pandemic, if you are running a business, you want that to be busy, okay? But you don't want to be too busy such that everybody get overwhelmed. And your employees will complain, why don't you hire more people? But if you hire too many people, then you spend too much money. Eventually, you have only less money left in your budget, and you may end up in need of sending some people home, and you will not make some people happy either if you do that. Okay, so if you can plan that ahead with and play with this probability, that will be great. It will make your people working for you, your staff, be happy. Okay, the customers will be happy because they get the service they need. Okay, they are not coming into empty rooms, but they are not coming to a room or a showroom or a store that's like so many people there. Okay, number 5. Now, starting from number 5 and on, I think how many more pages from here? 1, 2, 3. Oh, 3 more pages from here. Number 5. Assume the assets of credit unions are normally distributed with standard deviation $161 million. So the standard deviation is $161 million. And the credit union associated to 60 credit unions. So the association surveyed 60 credit unions and found their total assets to be the total assets to be 24,300 million. That's $24.3 billion. Find the point estimate mu, the mean assets for all credit unions. So the best point estimate is the sample mean, which is 24,300 million over 60. So the best point estimate is $405 million. That's the point estimate. Now, part B, construct a 95% confidence interval for mu. Step 1, best point estimate. We got that earlier on the top. That's X bar equals to 405 million. The critical value, we know the population standard deviation, right? So we will use standard normal, 95% in the middle. We need to find the critical value. So the area to the left of that is 95 plus the remaining 5% divided by 2 tail. So this will be 97.5%. Okay, so the critical value will be inverse norm 0.97501. That will be 1.95996. Step 2, how about margin of error? This is critical value times population standard deviation 161 over square root of 60. 1.95996 times 161 divided by square root of 60. That is 40.73779 in million. $1 million. So 95% confidence interval for the average assets of all American Credit Union Association will be best point estimate minus margin of error less than mu less than best point estimate plus margin of error. Okay, so 405 minus 40.73779, that will be 364.26221 less than mu less than 445,700.73779, and all of them in million. Part E. What sample size is needed to determine mu within $10 million with 92% confidence level? So the margin of error is 10. The confidence level is 92%. Okay, first we need to find the critical value. 92%. That's in the middle, right? Okay, so if this is the critical value here, the area to the left will be 92% plus half of the remaining 8. So that's 4%. So the critical value will be area to the left of that critical value is 4% plus 92%. That's 96%. That's inverse norm 0.9601. But Thomas, I thought the mean and standard deviations are 405 and standard deviation is 161. No. This is the inverse norm for z-score. We need to find the critical value in z-score first. Okay, that's why we use z-score, not x-score. Inverse norm 0.96. I get 1.75069. Now, then the minimum sample size n will be the ceiling of 1.75069 squared times standard deviation 161 squared over margin of error 10 squared. Okay. I get 794.45. Now we need 795 credit unions to reach that accuracy. The ceiling means we round up. Okay, the ceiling means we round up. Now the next 2 pages, now you know why this question is, this test has a lot of extra credit. Because this semester, Spring 20, I gave them 2 pretty much new question. Two pretty much new question that they never see in my old tests. And that's why also the reason I want to go over this test with you. Now, I think I just realized that my tests here is very similar to my fall 21. Very, very similar. Except the last 2 pages. So when you study till the end, okay? Study till the end. Let a survey of 50 Math 227 Test 2 score in Thomas's class in a confidence interval results in a confidence interval like this. Now, if sigma is known to be 12, find the confidence level by doing the following steps. The best point estimate will be the midpoint. You see, because best point estimate X bar is you plus the margin of error, you get this, you minus the margin of error, you get that, right? Okay, now this 54 is the lower bound, 62 is the upper bound. X bar is the midpoint. So midpoint formula, 54 plus 62 over 2, that will give you what? 58. Okay. Now then margin of error, part B, is the difference between upper bound and the midpoint. Or you can also use the midpoint and lower bound. Or you can also use the upper bound minus the lower bound divided by 2. Because the upper bound minus the lower bound, that's twice the margin of error, right? So after you subtract, divide by 2, you will get the margin of error, which is 4. Find the critical value. Find the critical value being used in that in their computation. Now we know the formula for margin of error is critical value z times standard deviation sigma over square root of n. Now we know from our computation above, margin of error is 4. Population standard deviation is given by 12. And sample size is what? 50. The sample 5 is 50, so this is square root of 50. So the critical value, z critical, will be 4 times square root of 50 over 12. Okay. I get critical value to be 2.35702. Actually, we can find the confidence level already at this point, because we know now that the confidence level is the area bounded by that critical value on the top and the opposite of that critical value at the bottom, right? So we can say confidence level equals to normal CDF negative 2.35702 up to 2.35702, 1. Yeah, you can do that already. I get 0.98157 158. Now, usually, if we make it confidence level, then we will write 98.16%. Okay, but don't round it. Don't round it. Usually, confidence level is expressed in percentage. That's what I'm saying. Okay. Now, if they do rounding, they usually round to only one decimal place, though, when it comes to, that's the practice, okay? In practice, they usually round to one decimal place when it comes to the confidence level, okay? Most of the time, they will just say this is 98% confidence level. Okay, but on paper, of course, we still need to write it as accurate as possible. Let the interpreter, the one who interpret the result, does the rounding. We, as the one doing the computation, don't do round. If you round to 5 decimal places in my class. Now, let's do part D. Before we did part C, I asked them to compute what is the area to the left and to the right of that C critical, which is 2.3 something earlier, 2.35702. What is the area to the left? What is the area to the left? And area to the right of that critical value. The area to the left first. Probability that Z, not X. Probability that Z less, because this number is the C score, right? That will be normal CDF. Negative E99. 2.3570201. I get 0.99079. That's the area, which is the probability to the left of that C score. How about the area to the right? Probability Z is greater than that. That will be normal CDF 2.35702 E99 01. Let me move that a little bit to the left. That will be 0.00921. Now, how do we use this then to find the confidence level? Well, you see that this region here is the same to the region here. If this were negative 2.35 something. So to find the confidence level, what you can do is you subtract the yellow one by the blue one. Okay, because the confidence level that we want is the area here. This is the confidence level. This is the area here, right? Okay, so what you can do is you get the yellow one, which covers this part here, minus the blue region, which happens to be that one, the same to that one. Okay. So the confidence level, according to the numbers we have above, is 0.99079 minus 0.00921. And you will see that's basically the same to what we have here. Okay, 0.98158. Okay. Last question. The length of an adult tuna fish be normally distributed with standard deviation 12. So sigma equals to 12. If the first quartile of the length of all adult tuna is 41, oh, what is that, Thomas? The first quartile. So the bottom 25% has the cutoff 41 inches. Find the C-score associated to the Q1. Find the C-score. Okay, let me use K instead. Such that the area to the left is 25%. The C-score, C-score. Okay, so K equals to inverse norm 0.25. The mean is 0, standard deviation of 1. That's the C-score, by the way. That's negative 0.67449. Now, so what happened is this. You have a normal distribution, okay, with known standard deviation. Okay, the standard deviation is known, so the variance is also known, but the mean is unknown. Can you find that mean? If they tell you that instead of the mean, they give you the first quartile is 41 inches. Can you find the mean? So we first find the C-score and then use the C-score formula. Okay, the C-score is negative 0.67449. That is equals to 41 minus mu over 12. Okay, the C-score associated to that 41 is negative 0.67449. We computed in part A. Now, can you reverse engineer that to find the mu? Now, to be honest with you, this last question is hard, such that in my tests in 420, I separate that becomes a take-home, a supplement. Okay, but to be honest with you, even after I give them 1 day extra, more than half of them still cannot do this. And the reason is because we do not have the prerequisite of solving equations anymore, like prerequisite intermediate algebra anymore when you take this course, which is in the past that's required. Okay, that's required. We don't require that anymore as a course, but it is assumed that you know how to solve equation. Okay, it is assumed that this is something you should have learned even before you come to college. Okay, now anyway, this will then be 12 times negative 0.67449 equals to 41 minus mu. That is negative 8.09388. So the mean will be 41 minus negative 8.09388. Okay, which is 49.09388. That's the mean. So this is the technique we use to find out the average height, or in this case, the average length, without measuring one by one. without measuring one by one. Okay, basically you can do the following. Imagine if you have a lot of tuna, right? A lot of tuna, a lot of them, and you just use one stick. Let's say that stick is 41 inches. Okay, and you found out that 1/4 of them actually less than 41 inches. 1/4 of them less than 41 inches. 1/4 of all tunas that you measure is less than 41 inches. Of course, the tuna that you measure has to be a lot, right? So instead of spending time measuring precisely the length of each tuna, you compare the tunas, how many of them, what proportion actually satisfy less than or equal to this 41 inches. Okay, now suppose 25% of them is less than 41 inches. Then we can find the mean from there. Okay, now at this point, we already see that the X, the tuna, is normally distributed with mean 49.09388 with standard deviation 12. Okay, now find the probability that a randomly caught adult tuna is longer than 60 inches. Probability that tuna is longer than 60. That's normal CDF 60, E99. The mean is 49.09388. Standard deviation 12. I get 0.18172. That's the probability. Last one. Find the probability that 10 randomly caught adult tunas, so we have 10, is longer than 60 inches on average. So the average length of 10 tuna will be, according to our theory, will be normally distributed with mean, this guy, and variance, original variance divided by 60. Oh, I'm sorry, not divided by 60, divided by 10. Because there are only 10 tunas, right? Not 60, my bad. It's 10. You want that to be longer than 60, the average to be longer than 50. That will be normal CDF 60 to infinity. The mean is 49.09388. The standard error, however, is 12 over square root of 10. And I get that's practically 0. I get this 2.92368 times 10 to the negative 56, which means the 2 is at negative. Oh, I'm sorry. No. I type it wrong. No. I type it wrong. Totally wrong. I need to type it again. 60 and then E99. The mean is 49.09388. Standard deviation, standard error 10 divided by square root of 12 divided by square root of 10. I'm sorry. Almost get it wrong. 0.00203. That's the probability. So it's very small, but doesn't mean it's impossible. Okay, now this is Spring 20 Math 227 Test 3. Big warning. Warning. This test only includes a confidence interval for mu with sigma known. Your test will include other confidence interval. Okay, not only the one for mu with sigma known, but also include confidence interval for mu with sigma unknown, confidence interval for proportion. Okay, I somehow think we had confidence interval for chi-square. Did we? No, we don't. No, we don't have confidence interval for chi-square, huh? For variance. No, we don't. Yeah. So the difference between spring 20 tests and fall 20, I believe, is there. Let me check. Let me check just to make sure. Give me a second. I clean up my browser first. Let me check fall 20 tests. Now, fall 20 tests, let me show you. Now, your test, the one I went over just now, is the same on the first page and the second page and the third page and the fourth page, the fifth page also. However, starting from page number 6, it's different. Yeah. In fall 20, I already include confidence interval for P, which we didn't have earlier. Okay. And confidence interval for population standard deviation. Okay. So I add them one extra questions from spring to fall 20. I give extra one question extra, but then for that reason, I push one question into supplement. Okay, now with your test, however, well, you basically need to know the one from fall 20 especially. Okay, the one from fall 20. Okay, right now it's 12:12. I'm done with what I want to do today. Okay, nobody interrupt me. Nobody even remind me earlier about that. My browser, the view was still at the discussion, so that we spend around 10-20 minutes with the incorrect view. Well, anyway, you figure out yourself. Okay, I will post the solution here together with those notes in our discussion board, and see you next week with the test. Okay, get ready with the test next week. Bye-bye.